Hello everyone, here is Afra. Today we are going to solve Cambridge IGCSE Physics Paper 4 Theory Extended, held on October-November 2018, and paper code is 0625 with variant 43. So let's start from question number 1. Question number 1. Figure 1.1 is the distance time graph for a moving car. Part A. On figure 1.1, mark a point P where the acceleration of the car is equal to 0. So going back to figure 1.1, we can see here that it's a distance time graph. Time is measured in seconds while the distance is measured in meter. So we have to describe the region where the acceleration is equal to 0. We can see on the distance time graph from time t is equal to 0 to 30 seconds, it is a straight line. It means that in this region, speed of the car is uniform. Means that when we increase the time, distance also increases. So in this region, here speed is uniform and we know that acceleration is equal to change in speed over change in time. So when the speed is uniform, it means that acceleration is equal to 0. Or we can simply say that in this case, when the speed is uniform, acceleration is equal to 0. So here we have to mark a point. So I write P at any point from 0 to 30 seconds. I write P here. And also erase this one. Going towards the next part. Part B. First, determine the speed of the car at time t is equal to 15 seconds. Here we have to find out the speed at 15 seconds. Again we can see here that from 0 to 30 it is a straight line, and in order to find out the speed we have to find out the gradient of distance time graph, because speed is equal to gradient, or it is also equal to slope of distance time graph. So from 0 to 30 seconds it is a straight line. We take any point on this line and find out the slope. It will be equal to the speed of the car. So I take any 2 points. I suppose that I take t is equal to 10 and t is equal to 20. So these meet the curve at this point, and I have to join both of these points with the distance and time axis. So using a ruler, so here we can see that when time equal to 10 seconds, distance is 50 meter, and when time is equal to 20 seconds, distance is 100 meter. So I write here speed is equal to gradient or it is also be called slope, and it will be equal to delta D over delta t, or I write d2 minus d1 over t2 minus t1. So there are 2 points, that is 20 and 100, and this point is 10 and 50. So using these 2 points, I find out the slope. I write here these 2 points, 10 and 50, and second point is 20, 100. So d2 is 100 minus d1 is 50 divided by t2 is 20 minus 10. It will be equal to 50 over 10, that is 5 meter per second. So the speed of the car will be equal to 5 meter per second. Part 2. The average speed of the car between time t equal to 30 seconds and time t equal to 45 seconds. Here we have to find out the average speed. Average speed is equal to total distance divided by total time. I write here average speed is equal to total distance covered by the car divided by total time taken. So we have to find out the total distance and total time. T equal to 30 and 45. So it will be at this point and at this point. We have to join this point with the graph so that we can find out the corresponding distance values. So here we can see that at time t is equal to 45 second, distance is 300 meter, and time t is equal to 30 second, distance is 150 meter. So taking these 2 points, I can find out the average speed. So it will be equal to 300 minus 150 divided by time is 45 and 30. So that it will be equal to 150 over 15, which is 10 meter per second. So 10 meter per second is the average speed of the car between t is equal to 30 second and t is equal to 45 second. I write here 10 meter per second. Part C. At time t is equal to 45 seconds, the car starts to decelerate. It means that at time t is equal to 45 seconds, the speed of car decreases. At time t is equal to 55 seconds and at a distance of 400 meters. From the starting point, the car stops. Then at t is equal to 55 seconds and distance equal to 400 meters, car stops and it remains stationary for 5.0 seconds. On figure 1.1, draw a possible continuation of the distance time graph. So first of all, there are 2 parts. At time t is equal to 45, car decelerate. It means that the speed decreases. Speed decreases means that gradient decrease. So when I draw it on the graph, it will be, and we have to draw it up to 400, and from 45 to 55 second, I think. Yes, from 45 second to 55 second. 55 second will be at this point, and distance will be 400 at this point. So the decreasing speed is actually represented by a curve just like this. So I draw the same curve here, starting from t is equal to 45. So this is car decelerating. And second part is that at time t is equal to 55 second and at a distance of 400 meter, it becomes stationary. Means that its speed is equal to 0 and it remains stationary for further 5 seconds. So this is 55 and it remains stationary for 5 seconds. So there will be a straight line that is parallel to time axis. I draw it. So you can see also that at this point distance is 400 meter and it remains stationary from t is equal to 55 to 60 seconds. So we have completed this part. Question number 2, part A. Complete figure 2.1 by writing in the right hand column the name of the quantity given by the product in the left hand column. So here is a figure 2.1 and we can see that on the left column there is product and on right column there is quantity. First of all, mass and acceleration. So which quantity is equal to the product of mass and acceleration? According to Newton's second law of motion, F is equal to ma. Means that force is the product of mass and acceleration. So it will be force. Force and time. So we know that acceleration is equal to change in velocity over time. I write here m v minus u over t, and when this t comes on this side it will be f cross t, which is equal to m v minus u. So we have to tell the name of this quantity, that is the product of force and time. So this is basically impulse. Impulse is equal to the product of force and time or the change in momentum. So I write here it is impulse. Part B. Figure 2.2 shows a man hitting a ball with a golf club. The ball has a mass of 0.046 kg. The golf club is in contact with the ball for 5.0 into 10 to the power minus 4 seconds and the ball leaves the golf club at a speed of 65 meter per second. Part 1. Calculate first the momentum of the ball as it leaves the golf club. Here we have to find out the value of momentum. We know that momentum, that is represented by P, it is the product of mass and velocity. I write here m and v. So the mass is given, that is 0.046 kilogram multiplied by speed, which is 65 meter per second, because we have to find out the momentum of the ball as it leaves the golf ball. And this is the speed when the ball leaves the golf club. That's why I multiply it with 65 meter per second, so that the momentum comes to be 3.0. The unit of momentum is kilogram meter over second, and it is also equal to 3.0 Newton second. Both are the unit of momentum and both are same. So I write here momentum is equal to 3.0 Newton second. Part 2. The average resultant force acting on the ball while it is in contact with the golf club. So here we have to find out the average resultant force. Using formula that product of force and time is equal to change in momentum mv minus u. So we have to find out the value of F. It will be equal to mv minus u over t, where t is the time. So the initial velocity of the ball is equal to 0. I write here u is equal to 0. So it becomes mv over t. mv is the momentum. I represent it with p over time. So by putting values, F will be equal to p over t. Momentum that we already calculate in part 1, 3.0 divided by time is given 5.0 into 10 to the power minus 4. 5.0 into 10 to the power minus 4 second. So the force comes to be 6000 Newton. This is the average resultant force. I write here average force is equal to 6000 Newton. Part 2. While the golf club is in contact with the ball becomes compressed and changes shape. State the type of energy stored in the ball during its contact with the golf club. So which kind of energy is stored in the ball when it compresses? So with the compression, there is the elastic energy. So when the ball compresses, there is elastic energy associated with the ball. So I write here its elastic energy. Question number 3. The density of mercury is 1.4 into 10 to the power 4 kilogram per meter cube. Part A. Figure 3.1 shows an instrument that is being used to determine the atmospheric pressure. So in the figure 3.1 we can see that there is a instrument and it is used to measure the atmospheric pressure. And height is given 760 millimeter and there is a space A and mercury is filled in it. Part 1. State the name of this instrument. So this instrument is actually barometer that is used to measure the atmospheric pressure. I write here it's a barometer or mercury barometer. Part 2. State what is in space A. Going back to figure, we can see that there is a space A that contains nothing. It is just like vacuum. So there is nothing in the space A. I write here it's vacuum. Part 3. Calculate the atmospheric pressure. Here we have to find out the value of atmospheric pressure. So I write here pressure, which is the product of density, acceleration due to gravity, and height or depth. So density is given, that is 1.4 into 10 to the power 4. So P will be equal to 1.4 into 10 to the power 4 multiplied by the value of G is 10 and height is given, that is 760 millimeter. So first of all we have to convert this into meters. I write here H is equal to 760 millimeter, and it is equal to 760 into 10 की power minus 3 meter, which is also equal to 0.76 meter. So I multiply 10 with 0.76 and the value of atmospheric pressure comes to be 1.1 into 10 की power 5 Pascal. So this is the value of the atmospheric pressure. I write here 1.1 into 10 की power 5 Pascal. Going towards the next part B. Figure 3.2 shows mercury stored in a cylindrical glass jar of internal radius 4.0 centimeter. The depth of the mercury in the jar is 12 centimeter. Calculate the weight of mercury in the jar. Here we have to find out the value of weight of the mercury that is in the jar. So in figure 3.2 we can see that there is a jar which is filled with mercury and the depth is 12 centimeter while the diameter is 8.0 centimeter. So we know that weight, it is the product of mass and acceleration due to gravity g. We know that the value of g is 10 meter per second square, but we don't know the value of mass. So first of all, we have to find out mass. In the start, value of density is given. So we know that density is equal to mass over volume. By using this formula, we can calculate mass. It will be equal to product of density and volume. For that, we have to know the formula of volume and it will be equal to pi r square into L, where r is the radius and L is the depth. So I write here rho pi r square and L. So the mass will be equal to, density is given, that is 1.4 into 10 की power 4 multiply by pi, which is 3.14, and radius. It is given that the internal radius is 4.0 centimeter and we have to convert this radius into meters. So I divide it by 100 and it becomes 0.04 meters. So it will be 0.04 square multiplied by depth. Depth is given 12 centimeter and we also have to convert this into meter. It will be 12 over 100 and 0.12 meter. So I multiply it with 0.12. So this is the value of mass and we have to put this value into equation of weight, so that weight becomes 1.4 into 10 की power 4 multiply 3.14 and 0.04 square multiply by 0.12 and value of g is 10 meter per second square, so that the value of weight comes to be 84 Newton. So I write here weight is equal to 84 Newton. Question number 4. A wave is traveling across the surface of water in a tank at a speed of 0.15 meter per second. Part A. The wavelength of the wave is 0.030 meter. Calculate the frequency of the wave. Here we have to find out the frequency of the wave when wavelength and speed is given. So using the relation V is equal to F lambda, we have to find out frequency that is represented by F. It will be equal to V over lambda. V is 0.15 divided by lambda is 0.030. so that the value of frequency is equal to 5.0 Hz. I write here frequency is equal to 5.0 Hz. Part B. This water wave is a transverse wave. Explain what is meant by the term transverse wave motion. So first of all, in the transverse wave, particle of the medium moves in the direction perpendicular to the direction of propagation of the wave. If I consider that I produce vibration up and down and wave travel from left to right, so we can see that the vibration direction is up and down while the wave travel in this direction. Both of these are perpendicular to each other because there is an angle of 90 between them. So this kind of wave is transverse wave and its motion is transverse wave motion. So first point is that in transverse wave, vibration of particles is perpendicular to the direction of wave travel. Second point is that this wave consists of crust and trough. So I write here, it consists of crust and trough. And third point is that it transfers energy and not matter. Next, part 2. Draw a diagram that represents a transverse wave traveling from left to right across the page. On your diagram, label wavelength and the amplitude. First of all, we have to draw the transverse wave and then we have to label the wavelength and amplitude. So again, using ruler, I draw a line here. So it's a transverse wave. It consists of two portions. If I consider that it's a mean line, the portion of the transverse wave above this mean line is crust, while the portion of the wave below the mean line is trough. And we have to label the wavelength. Wavelength is a distance between two consecutive crust and trough. I write here distance between two consecutive crust or trough. So the crust start from this point and second start from this point. So this distance is basically equal to wavelength. I label it so this is wavelength. Second, we also have label amplitude. So amplitude is the maximum distance from the main line. So I will label it as so this is amplitude. I write here question number 5 part A. A student is supplied with a small block of iron, a thermometer and an electrical heater of power T. So there are three things. First of all, a small block of iron, thermometer that is used for the measurement of temperature, and the electrical heater whose power is P. There are two holes drilled in the iron block. The heater fits tightly into one hole and the student places the thermometer into the other hole. Figure 5.1 shows the equipment. So we can see here that figure 5.1 contains iron block, thermometer, cables and heater. The student uses this equipment when determining the specific heat capacity of iron. State the other equipment that the student will need, the measurements the student need to take, and the equation used when calculating the value of specific heat capacity of iron. So this experiment is basically for the measurement of specific heat capacity of iron, and it is given that the heater has power P. But for the calculation of specific heat capacity, we need energy. So in order to calculate energy, we know that power is equal to rate of transfer of energy. So energy will be equal to P cross T, means that power and time. So in order to calculate time, we need timer or stopwatch. And for the measurement, we also need balance and power supply. So I write here the other equipments are stopwatch, or timer, for counting time, and there is also a balance or scale, and power supply. Part 2. The measurements the student need to take. So we know that energy supplied will be equal to mc delta T, and C will be equal to E over m delta T. So we can measure energy by power and time, but we also have to know about mass and change in temperature, where delta T will be equal to final temperature minus initial temperature. So we also have to know about this temperature. So the measurements that student need to take is measuring the mass and also initial and final temperature. So I write here measurements of mass of iron block and initial and final temperature. Part 3. The equation used when calculating the value of specific heat capacity of iron. So which equation we use here? By seeing this equation, here is energy, but we have to write in terms of power. We can use both of these, so it will be P cross T divided by M delta T. Both of these are used for the calculation of specific heat capacity. So I write here the equation is I write here C is equal to E over M delta T, which is also equal to Pt over M delta T. Part B. In the student's home, there is a wood burning stove which is also made of iron. The mass of the wood burning stove is 85 kg. Part 1. State what is meant by the thermal capacity of an object. So what is the thermal capacity of object? It is the energy required to increase the temperature per degree C. So I write here the energy required to increase temperature per degree C. Part 2. The specific heat capacity of iron is 460 joule per kg per degree C. Calculate the thermal capacity of the wood burning stove. Here we have to calculate the thermal capacity when the specific heat capacity and mass is given. So we know that thermal capacity is the product of specific heat capacity and mass. I write here capital C is for thermal capacity. It will be product of mass and specific heat capacity. So it will be 85 kg multiplied by 460, and it comes to be 3.9 into 10 की power 4 joule per degree C. So the value of thermal capacity will be equal to 3.9 into 10 की power 4 joule per degree C. Question number 6. Part A. Figure 6.1 shows white light incident at point X on glass prism. So here is a figure 6.1. We can see that there is a glass prism and a ray of white light is incident at point X on the prism, and there is also a screen that is placed on the other side of the ray of white light. Part first. From point X on figure 6.1, draw a ray of red light labeled R and a ray of violet light labeled V to show how a spectrum is formed on the screen. So here we have to form the spectrum on the screen by drawing the path of red light and violet light. So first of all, there are two lights, red and violet. Red light has longer wavelength as compared to violet. It is longer, and for violet it is shorter. So the light that has shorter wavelength will bend more. So in this case, bending will be more. But for the case of red light, the bending will be small. Now first of all, I draw the path for the red light, and first of all we have to draw the normal at the surface in order to draw the path of the red light inside the prism. So this is normal ray here, and we can see that ray of light is going from less denser medium to denser medium. So the medium that has less density is basically rare medium, and the medium that has large density, it is known as denser medium. So first of all, when the ray of light goes from rare to denser medium, it will bend towards normal. But if the ray of light enters from denser into rare medium, it will bend away from normal. So in this case, we can see that the ray of white light is coming from rare to denser medium. So the ray inside the prism will bend towards the normal. So I will draw its path. Sorry, it's red light. So in this way, it bends towards the normal in such a way that this is angle of incident and this is refraction. So that the angle of incident must be greater than angle of refraction. Now in order to draw its path out of prism, I again use the normal ray here. It is the normal ray to this surface. Now here we can see that the ray of light coming from denser to rare medium, so it will bend away from normal. If this is the angle of incidence, then the angle of refraction must be larger because the ray bent away from this normal, just like this. So this is a complete path for the red light. It is angle of refraction, and here we can see that angle of incidence is smaller as compared to angle of refraction. So we also have to draw the path for violet light. So I erase these normal rays. Now the bending for the case of violet light will be larger as compared to red. So I will draw its path. The bending will be more. And at this point, I again draw the normal path. So it is the normal ray here, and we can see here that this ray is coming out of prism, means that coming into the rare medium, so it will bend away from the normal. So I will draw its path. It will be like this. So this is a path for the violet light and red light. Now I erase this normal ray from here and put arrows. Going towards the next part B. Going towards the next part 2. State the color of the light in the visible spectrum with the shortest wavelength. So the shortest wavelength is for violet light because red has the longest wavelength. Part B. The critical angle for a type of glass is 42 degrees. Figure 6.2 and figure 6.3 shows the two prisms ABC and PQR made of this type of glass. A ray of monochromatic red light passes into each of the prism. So here is the figure 6.2, and we can see that a ray of light coming and it incident on the face AC, and then it reflect into downward direction. But in figure 6.3 we can see that a ray of light comes and it falls on the face PR, and there will be the bending, that is the refraction, and also the reflection. Part first, state what is meant by monochromatic light. So monochromatic light is basically a light of single wavelength or single color or single frequency. So I write here a light of single frequency. Next part 2. Describe and explain what happens to the ray of light in figure 6.2 as it strikes side AC of the prism. So going back, it's a face AC and ray of light falls on this face, and we can see that it bends in downward direction. It means that there is totally internal reflection. There is no refraction. So when a ray of light comes and it falls on AB face, then there will be total internal reflection. I write here total internal reflection at face AC. and there will be no refraction. And in this case, the angle of incidence must be larger than critical angle. That is the condition for total internal reflection. Part 3. Describe and explain what happened to the ray of light in figure 6.3 as it strikes the glass at point Y. So going back to figure 6.3, we can see here that a ray of light comes and it strikes at point Y, and there will be the refraction and also the reflection. So I write here, some of the light reflect and some of light refract at point Y. Because here in this case, angle of incidence is smaller than critical angle, and some light also reflect. Question number 7. A defibrillator is a machine that sends an electric charges through the heart of the patient whose heart is not beating correctly. Doctors learn to use the defibrillator by practicing on a medical dummy. Figure 7.1 shows the two contacts of defibrillator attached to the medical dummy. The contact that touches the dummy are made from metal, and when the defibrillator is being used, one contact becomes strongly negatively charged and the other contact becomes strongly positively charged. The handles of the contact are made from the plastic, which is an electrical insulator. Part A. First, state how the structure of the electrical insulator differs from the structure of conductor. So here we have to differentiate between the structure of conductors and insulator. So we know that conductors contains a large number of free electrons, while there is a lack of free electrons in the insulators. The electrons in the insulators are fixed in their position. So I write here, no free electrons in the insulator, are electron fixed in its position. Part 2. Suggest why the handles are made from an electrical insulator. So electrical insulator does not allow the flow of free electrons because it does not have free electrons. So there will be no current in the insulator, and the handles made from the electrical insulator to stop the flow of charges so that doctor does not receive an electric shock which might be injured for him. So I write here, handles are made from electrical insulator to stop the flow of charges so that doctor does not receive an electric shock which might injure him. Part B. Explain in terms of the particles involved how one contact become negatively charged and how the other contact become positively charged. So first of all, if I consider that this is contact 1 while this is the contact 2. So here we have to explain that how one contact become positively charged while the other become negatively charged. So the electrons move from one contact into another. So if I suppose that it is contact 1 and it is 2 and electrons move from contact 1 into contact 2. So that on the contact 1 there is deficiency of negative charges. So it becomes positively charged. While the contact 2 that receives the electron, it has a large number of electrons, so it becomes negatively charged. So we can simply write that electrons move from one contact into another. And negative contact gains electron. While positively charged contact losses electron. Part C. The defibrillator passes a charge of 9.1 into 10 to the power minus 3 coulomb through the medical dummy in 6.5 into 10 to the power minus 4 seconds. Calculate the average current in the dummy. Here we have to find out the average current when total charges and time is given. So we know that basically current is the rate of flow of charges. I write here I is equal to Q over T. So charges are given, that is 9.1 into 10 to the power minus 3 coulomb. And time is 6.5 into 10 to the power minus 4. So the value of current comes to be 14 ampere. I write here current is equal to 14 ampere. Question number 8. A 9.0 volt battery is connected to a 120 ohm resistor in series with wire P. Figure 8.1 shows the voltmeter connected across the 120 ohm resistor. So here is a figure 8.1 and we can see that there is a battery whose voltage is 9.0 volt and there is also a wire P that is connected in this circuit and a resistor whose resistance is 120 ohm and across this resistor we have connected a voltmeter that is used to measure the potential difference. Part A, state the energy changes that are taking place in the circuit. So first of all, we know that in the battery there is chemical energy, and this energy is used to drive the charges across the whole circuit. So this kind of energy must changes into heat energy, and this must dissipate across different components like resistor. So we simply say that the chemical energy changes into thermal energy. I write here chemical energy changes into heat or thermal energy. Part B, the reading on voltmeter is 2.4 volt. Calculate part first. The current in 120 ohm resistor, we have to find out the current in 120 ohm resistor when the reading on voltmeter is 2.4 volt. So first of all, using Ohm's law, that is V is equal to IR, and we have to find out the value of I will be equal to V over R, where V is 2.4 volt and R is 120. So the value of current comes to be 0.02 ampere. So this is the value of current in 120 ohm resistor. I write here current is equal to 0.020 ampere. Part 2, the potential difference across the wire P. Here we can see that this is our resistor, and across this resistor in series we have connected a wire P, and we have to find out the potential difference across the component P. So first of all, the reading on voltmeter is 2.4 volt. It means that 2.4 volt is the potential difference across 120 ohm resistor. And we can see here that the battery, wire P and resistor are series, and in the series combination the potential difference changes, or we can simply say that the potential difference of battery must be equal to the potential difference across different components. So I write here potential difference of battery, it will be equal to potential difference of resistor plus potential of wire. Here we have to find out the potential of wire, so I write it will be equal to V of battery minus V of resistor. So the potential difference of battery is 9.0 minus potential difference of resistor is 2.4. So the potential across the wire P comes to be 6.6 volt. I write here 6.6 volt. Part 3, the resistance of wire P. Here we have to find out the resistance of wire P, and we already calculate the potential difference across wire P. And going back, here we can see that these are in series combination, and in series potential difference changes but current remains same. I write here in series current remains same but voltages or potential difference changes. It means that current that is passing through 120 ohm resistor is same as that of the value of current that is passing through the wire P. So again using Ohm's law, I write here V is equal to IR and R is equal to V over I. So potential difference across the wire P that we already calculated is equal to 6.6 divided by current that is across 120 ohm resistor. Its value will be equal to the current across wire P. So I write here 0.020. So the value of resistance comes to be 330 ohm. I write here 330 ohm. Part C. Wire P has a diameter D and length L. A second piece of wire Q is made of the same material as P. The diameter of the wire Q is 0.50 multiplied D and its length is 5.0 into L. Calculate the resistance of wire Q. Here we have to find out the resistance of Q wire. So again using that, resistance is directly proportional to length and it is inversely proportional to area. By combining both of these equations, resistance will be proportional to L over A, or we can write R is equal to rho L over A. Here rho is resistivity, L is length and A is area, and here we have to find out the resistance of wire Q. So first of all I write this formula for wire P. So R will be equal to, here we can see that there is a diameter. So we have to write this formula in terms of diameter, and we know that area is equal to pi R square. So it will be rho L over pi R square, where R is the radius. So I also write it as rho L over pi, and radius is half of the diameter. So I write here D over 2 whole square. It will be 4 rho L over pi D square. So we have write the formula of resistance in term of diameter. Now I write this formula for wire P. It will be 4 rho L over pi D square. And we know that previously we have solved this question for wire P, and we also have to find out the resistance of wire P, that is equal to 330 ohm. So just write here it is equal to 330 ohms. Now I write for wire Q, RQ will be equal to 4 rho L prime over pi D prime square. We can see here that Q is made of the same material, means that the material of both wire is same, so that the resistivity of both wires will be same. Now the length of Q wire will be L prime, that is given 5.0 into L, and for diameter D prime it will be equal to 0.50 D. So putting these values here, RQ will be equal to 4 rho 5.0 L over pi 0.50 D squared. By rearranging it, I get 5.0 over 0.50 square and 4 rho L over pi D square. So this factor is basically equal to Rp, and the value of Rp is 330 ohm. So using this value here, it will be 5.0 over 0.50 square multiply by 330. So that the value of resistance of wire Q comes to be 6600 ohms. I write here resistance is equal to 6600 ohms. Question number 9, part A. Describe how a direct current DC differs from an alternating current which is also be AC. So here we have to differentiate between the direct current and alternating current. So the direct current is one that has constant value, or we can simply say that direct current flows in one direction and it does not change its polarity. So I write here DC flows in one direction and does not change its polarity. Part B. Figure 9.1 shows how the voltage output of an alternating current generator varies with time. So here is a figure 9.1 and we can say that voltage is taken along y-axis and it's a voltage output of alternating current generator and it is sinusoidal varying. A heater is connected directly to the AC generator and the maximum current in the heater is 0.75 ampere. Part 1st. On figure 9.2, sketch a graph to indicate how the current in the heater varies with time. Here we have to draw this graph for the current that varies with the time. So first of all, the current is also sinusoidal as voltage and both of these must be in phase. So first of all, here maximum value of current is given, that is 0.75. So it will be at this point 0.75 and at minimum value minus 0.75. We can see from here that graph starts from this point and then it passes through 0.2 at mean position and after that again at 0.6 mean position, and there is also the mean position at 1.0. So first of all I put the dots. At 0.20 it is mean position, again at 0.6 and 1.0. And we can also see that in the start the voltage is at positive peak. It means that in the start the current should be plus 0.75 and here current should be minus 0.75. Now I have put the dot here and we So this is the complete sinusoidal wave which shows that how the current varies with time. Going towards the next part 2. Calculate the power produced by the heater when the current is 0.75. So here we have to find out the value of power. We know that power is the product of current and potential difference. Here current is given, that is 0.75 and potential difference is not given, that is voltage, and we have to find out it from the graph. We can see here at this point the value of voltage is 7.2. So I write here 7.2. So the value of power comes to be 5.4 watt. Power is equal to 5.4 watt. Part C. Figure 9.3 shows the coil ABCD of the AC generator between two magnetic poles. Part first. On figure 9.3, draw a straight arrow to indicate the direction in which the side AB of the coil is moving. Label this arrow M. So first of all, we can see here in figure 9.3 that the direction of rotation will be clockwise. It means that there are two forces. One is acting in this direction and other is acting in this direction, due to which this coil rotates. So we can simply say that on the side AB, the force is acting vertically upward, while the force on side CD is in downward direction, due to which the coil rotates in this direction. So I will erase this, and here we have to draw the direction in which the side AB of the coil is moving. It means that coil is from AB side is moving in upward direction, and we have to label it with M. So I will draw this. So this is the direction in which the side AB of the coil is moving. Part 2. Deduce the direction of the current induced in side AB of the coil and explain your reasoning. So here we have to describe that in which direction the current is induced inside AB. So here we can see that the magnetic field direction is from north to south, and the force acting here is vertically upward. And we have to find out the direction of current flow. By using Fleming left hand rule, I can find out the direction of flow of current. I write here Fleming left hand rule. According to this rule, if I put thumb, forefinger and middle finger of my left hand mutually perpendicular to each other, so that the forefinger points out the direction of magnetic field while the middle finger points the direction of current, then my thumb will indicate the direction of force. I write here thumb is in the direction of force and forefinger is in the direction of magnetic field, and middle finger shows the direction of current. By using Fleming left hand rule, I see that the current on the side AB is flowing from A to B like this. So it is the direction of current on the side AB. I write here using Fleming left hand rule, if thumb, middle finger and forefinger are perpendicular to each other, Then thumb finds the direction of force forefinger direction of magnetic field and middle finger is the direction of current. That is from A to B. It means that the current in side AB will be from A to B. Part 3. The rate at which the coil of the AC generator rotates increases. State two ways in which the alternating voltage changes. So, how we can change the value of alternating voltage? So, we can change the alternating voltage by changing the direction more often. I write here changing direction more often, and second one, we can increase the alternating voltage by decreasing the time period or increasing frequency. So I write here maximum voltage, that is alternating voltage, when time period is small or frequency is large. Question number 10. Thorium 234, whose symbol is Th and atomic number is 90 while the mass number is 234, is radioactive. It decays by beta emission to form an isotope of protactinium Pa. Part A. Complete the nuclide equation for this decay. Here we have to complete this equation, and it is Th, that is thorium, with atomic number 90 while the mass number is 234, and it undergoes beta decay and changes into protactinium. So first of all, we know that beta particle is just like electron. These are like electrons with 0 and -1, means that atomic number is -1 while the mass number is 0. In order to find out the proton number and nucleon number of the protactinium, we have to check the atomic number and mass number on both sides of this arrow. So first of all, I write here mass number. On the left hand side, mass number is 234, so it will be 234, it will be equal to beta particle has mass 0 plus, I write here first of all x and y, and I have to find out x. So in this case, x will be equal to 234. It means that the mass number of protactinium is 234. I write here it's 234. Now I also have to find out the atomic number. On the left hand side, we can see atomic number is 90. It will be equal to y plus, here atomic number is -1, so it will be -1. So the value of y will be equal to 90 plus 1, that is 91. So that y will be equal to 91. By seeing this nuclear equation, we can say that the atomic number changed by 1 or it is increased by 1 while the mass number remains same, that is 234 in this case. So it is a complete nuclear equation for the decay of thorium into protactinium with the emission of beta particle. Going towards the part B. A pure sample of thorium-234 emits beta particles at a count rate of 2480 counts per second. The half-life of thorium-234 is 24 days. Calculate the count rate for the emission of beta particles from the thorium in the sample after 72 days have passed. So here we have to calculate the count rate. For that we have to know that how many half-life passes. So I just write here number of half-lives will be equal to total time, that is 72, divided by half-life. So here total time is 72 days and half-life is 24 days. So it becomes 3 half-lives. It means that 3 half-lives passes. So initially it is given that sample count rate is 2480. I write here count rate and here is half-life. So when first half-life passes, then this amount remains half. So I write here 2480 divided by 2, it will be 1240. So the count rate after first half-life reduces to 1240 count per second. After second half-life, it becomes half of this value and it will be 620. And after third half-life, half of 620 remains left, so it will be 310. It means that when 3 half-life passes, then there will be 310 count rate per second. So the count rate will be equal to 310 counts per second. Part C. The isotope of protactinium in part A is also radioactive. It decays by beta emission and has a half-life of 70 seconds. State and explain how this would affect the observed count rate for the sample in part B after 72 days. So here we can see that protactinium is highly radioactive as compared to thorium, and its half-life is much shorter as compared to thorium, because you can see here its half-life is 70 seconds while the half-life of thorium is 24 days. So it is very short as compared to the half-life of thorium. So that's why the count rate is larger than 310 count per second for protactinium. I write here protactinium is highly radioactive and its half-life is much shorter as compared to thorium, whose symbol is Th. So count rate for protactinium is larger than 310 counts per second. It means that the count rate for protactinium should be larger as compared to the thorium.